Welcome. Thanks for joining us. I'm Jennifer Dunn. I'm a professor at the Santa Fe Institute. And before I introduce Mark, I'd like to wish Murray Gelman a very happy birthday. I think he turned, sitting here in the front row, I think he turned 18 or something today. I forget exactly what, some combination of those numbers. Anyway, it's my pleasure to introduce Mark Newman for his second of 3 Santa Fe Institute Ulam lectures on Our Small World, How Networks of People and Information Shape Our World. Mark is the Paul Dirac Collegiate Professor of Physics and a member of the Center for the Study of Complex Systems at the University of Michigan. And he is one of the world's foremost experts and authorities on networks. His work on the fundamentals of network theory and its applications began to take shape during his postdoctoral fellowship at the Santa Fe Institute in 1996 to 1998, and continued through his appointment as a professor there, where he now also serves as on the science board. So last night, for those of you who are here, Mark gave an excellent and stimulating introduction to our connected world. He clearly explained what networks are and gave very interesting examples of technological, information, biological, and social networks. He also described how such data is painstakingly compiled and put together. And as someone who works at the intersection of ecology and networks on food webs, I know how difficult it can be to collect and compile really good, detailed network data. Tonight, we will hear Mark talk about what networks can tell us about the world. In other words, what we can do with all of the network data that he presented last night. Mark has made many fundamental contributions to our understanding of how networks are structured, and he will open a window on some of those insights during his talk tonight. While most of Mark's scores of papers that deal with basic theory and analysis related to the structure of networks, last night he mentioned some of his interesting applications of network research. For example, political networks of the U.S. House of Representatives and sexual networks on which epidemics can spread. And you'll hear more about epidemics tomorrow night. But before he comes on, I wanted to mention one other paper which many Americans would find of interest, especially starting at this time of the year. The title of that paper is A Network-Based Ranking System for American College Football. So the next time you glimpse a football game on TV, you can think back to its unlikely connections to the set of Santa Fe Institute Ulam lectures on networks by Mark Newman.
Thank you very much, Jennifer, for that very nice introduction. So as she mentioned, this is the second of these 3 Ulam lectures, and the topic is networks. I was going to start by giving a brief summary of the things that I talked about last night, but Jennifer already did that very well for me. But just in case you didn't make it last night, what we talked about is sort of what is a network. Answer is it's a bunch of dots connected together by lines. The jargon is we call the dots nodes and we call the lines edges. I know that's kind of jargony, but it comes up all the time. Everybody does it, so get used to it. Why are we interested in networks? Because they can represent all sorts of things in the real world. For instance, they can represent technological networks like the internet, information networks like the World Wide Web, a network of web pages connected together by hyperlinks, biological networks such as food webs that Jennifer studies, and social networks, which are networks of people, for example, who's friends with whom or who knows whom. I describe some examples of these networks, how we measure things about them, and some of the things that we found out by looking at networks. And now, tonight, I want to say something about what can we do with all this stuff that we've learned about all these different networks in the world. I want to give you some examples of interesting things that we've discovered by taking the networks that we've measured and looking at them more carefully. So, here's one example of a simple thing that we can do once we know about networks. Suppose that you have some network. You take a look at a network like this. This is actually a social network. And you can clearly see that not everybody in this network is equal. There are some people who are in the thick of things here in the middle of the network, and then there are other people who are sort of more peripheral around the edges of the network. So then you might look at this and ask yourself, well, what can I say about how central or important different people are in this network. Some people are going to be sort of well-connected in the middle of the network, and some people are going to be less well-connected people. So this leads us to an idea that network analysis refer to as centrality. Centrality is this idea of which is the most important node in a network, who is the most important person in a social network, or in the web network, what's the most important web page. Well, of course, the answers to these questions depend strongly on what you mean by important. There are various different ways that a person could be important in a social network. But to give you one example, suppose I could be thinking of distances in a network and who's close to whom within the network. So if I'm connected to somebody else in a network, there's a direct connection from me to you, then you're one step away from me in the network. I know you. If you have some friends that I don't know, then those people are 2 steps away from me in the network. I have to go 1 step from me to you, and then 1 step from you to your friends. So those people are still quite close to me. I could get in contact with them if I had to, but they're further away from me than you are. So there's this concept of distance in a network, and one way I could think of being well connected in a network is I'm looking for somebody who is not very far from everybody else in the network. So this leads us to consider this idea of distances in a network. So let's take a little moment to consider this idea of distances in a network. This is something that people have studied in networks for a long time. In fact, one of the most famous experiments done on social networks was an experiment done by Stanley Milgram in the 1960s, which is often referred to as the small world experiment, and possibly you've heard of this experiment. So that's a picture of Stanley Milgram over there. He was, at the time, a professor at Harvard University, and even if you haven't heard of this experiment, you might have heard of Stanley Milgram for another reason. He did another set of experiments, now considered rather notorious, about obedience, in which he got experimental subjects to press a button which allegedly gave an electric shock to another person that they could see through a glass window in another room. It was all faked. Nobody actually got an electric shock. It was just an actor pretending. But the person who was pressing the button didn't know that. And what they discovered in this experiment is that if an authority figure tells you you should press this button, in this case, a Harvard University professor, then a lot of people will do it, even though they know that they shouldn't do this. I mean, it's clearly a bad thing to do, right? You shouldn't press the button and give the person the electric shock, but a lot of people, it turns out, will. So this series of experiments taught us some rather disturbing things about people's response to authority figures. It also ended up getting Stanley Milgram fired from Harvard University because it is clearly a deeply unethical experiment. I mean, obviously this is a bad thing to do. I mean, the poor people who participated in this experiment, apparently some of them were in therapy for years afterwards. So that's probably the most famous thing he did. But before he did that experiment, he did this other experiment, which is really quite clever. So what he did in this experiment, he was interested in these paths through networks. How close are people to other people? How many handshakes are you away from another person in a network? So he did a clever experiment to determine this. He sent letters to a bunch of people, and he asked those people to get the letters to a target person who was a friend of his, who was a stockbroker who lived in Boston. The majority of the people were chosen from the city of Omaha, Nebraska. Some of them were also people in Boston. And so he sent them this letter, and he said, well, you have to get this letter to this target person. But the catch is you can't just send it straight to the target person. You can only give it to somebody that you know on a first-name basis. So you probably don't know the stockbroker in Boston on a first-name basis, but so what you have to do is you have to think, do I know somebody who's closer than me to this target person? And I could pass it to them, and then maybe they can pass it along and get it to the target person. So that could mean closer in a real geographic sense, like maybe you know somebody who lives in Boston or somebody who lives in Massachusetts, or it could mean closer in some social sense, like you might know somebody else who works in the financial industry or something like that. Anyway, you get to choose whatever you do, and then you pass the letter along, and then the next person repeats the exercise and decides to pass it along, and so the letter hops through a succession of acquaintances in this way. But the letter is basically surfing across the social network from acquaintance to acquaintance, and the hope is that eventually it will reach the target person, the stockbroker in Boston. It turned out, in fact, that most of the letters did not get there. Perhaps not a big surprise. People get this thing in the mail and they say, what is this? And they chuck it in the trash. But a small number of them, 64 letters, about 29%, did arrive at the target person. And so the famous result, which you may have heard of, is it took, on average, about 6 steps for those letters to get from, random person in Omaha, Nebraska, to a stockbroker in Boston. This is the origin of this famous expression, the 6 degrees of separation, this idea, sort of almost mythical now, that you are 6 handshakes away from everyone else in the world. So you can play this with yourself. Here's an example. Here's me, and I'm going to connect me to the President of the United States. Turns out to be not that difficult to do. I went to college with a woman called Karen Ruff, whose father was Chuck Ruff. There he is. He is a lawyer. Well, he was. He's dead now. But he was a lawyer working in Washington, D.C., and he was one of the defense lawyers for Bill Clinton in his impeachment trial. And Bill Clinton knows Barack Obama. So there you go. 3 steps. 1, 2, 3. And you've got from me to the President of the United States. Terrific. Okay, but now here's the catch. You all know me. So that means you're 4 steps away from the President of the United States, because you know me, and then there's 3 steps, and you get to the President of the United States. See, this is how it works. This is why it's such a small world. To put this in slightly more mathematical terms, here's how it goes. Suppose every person knows 100 people. That means the number of people 1 step away from you, people 1 degree of separation away from you, is 100, just all the people you know. All of them know 100 people, so the number of people 2 steps away from you is 100 times 100, which is 10,000. 3 steps away, 100 times 100 times 100, which is 1 million. Then you've got 100 million, then you've got 10 billion, but that's actually more than the total number of people in the world. There are only 7 billion people in the world, so we've got all of them, and we only had to go 5 steps. Okay, so it was 5, not 6, but this is the basic idea that as you go out from your starting point, it grows incredibly fast. This is actually what we call exponential growth. It's going up by a factor each time. It grows so fast that it doesn't take that many steps before you've got to everybody in the world. This is sort of the basic mathematical origin of the small world effect. So as I say, this is a result that has become a part of the folklore now. Pretty much everybody has heard of this thing. For instance, there's this popular parlor game, The 6 Degrees of Kevin Bacon. Maybe you've heard of this game. It's a game where you try and connect movie actors to Kevin Bacon in some small number of steps. And what's the connection between movie actors? It's who's been in a movie with who else. So, for instance, Clint Eastwood was in The Bridges of Madison County with Meryl Streep, and Meryl Streep was in A River Wild with Kevin Bacon. There, 2 steps, and I've got from Clint Eastwood to Kevin Bacon. And it turns out you can do that with almost any actor. It's not because Kevin Bacon's special, of course. You could do this. It doesn't matter who you're aiming for. You can do this starting with almost any actor. And what you're doing is you're surfing the network of movie actors, and the reason it works is because the small world effect is in play. You've got this 6 degrees of separation effect. So you can play this game. People have a lot of fun with this. There's all sorts of things that you see in the papers. Kevin Bacon linked to Al-Qaeda. Only 6 steps there. Well, of course it's only 6 steps. That's the whole point. Everybody's connected to everybody else in 6 steps. All right. Very good. So this movie actor network is actually kind of a fun example because it turns out to be very well documented. I mean, it's not, this is not a serious example, but there's this thing called the Internet Movie Database. It's a website that contains data about every movie, pretty much, ever made, including who was in the movie. So you can tell who's been in movies with who else because all the data is there. So you can go and actually assemble the entire network of which actors have been in which other movies. Here's a small portion of it that I made a plot of just for this talk. Here's 50 or so famous actors, and these are the connections between them, who's been in movies with who else. This is actually kind of an interesting network. I noticed after I'd made it that you notice there's this sort of separate group over here on the right, which is like Audrey Hepburn, Cary Grant, Clark Gable, Spencer Tracy. These are all the old-timers. And then this group over here is sort of more modern movie actors mostly. And it seems like, for some reason, Gregory Peck is the pivotal connecting person who connects the old school black and white to new. I have no idea why that is. Anyway. So, you can assemble this entire network here. And so now let's get back to the topic we were talking about to begin with, this idea of centrality. Who's the most important person in the network? So one way you could do that is you could say, well, if I can calculate the distance through the network from everybody to everybody else, then we could calculate the centrality of a person as being the average distance from you to everyone else in the network. So we're looking for people who, on average, they don't have to go very far through the network to get to anyone else. So this is one possible definition of being an important person in the network. You know, you don't have to go very far through the network to get to anybody else that you want to talk to. So you're a well-connected person. Well, you can calculate that kind of thing, and I did it, for example, for this movie actor network, just because we happen to have all the data. So this is a thing we call closeness centrality. It's defined as the average distance to everyone else in the network, and it's good if it's small, because you want to be a short distance away from everyone else. So here are the people with the smallest average distance to other people in this movie actor network. The person with the shortest average distance, the most central person in the movie actor network, is Christopher Lee. Do people know who Christopher Lee is? No? Yeah, he's slightly obscure, actually. He's this guy. He's a B-movie actor who was in a lot of bad horror movies where he played, you know, versions of Dracula and stuff like that. More recently, he's actually been in a couple of better movies. He also played a wizard in The Lord of the Rings and a Jedi Knight person in one of the new Star Wars movies. Anyway, so he was top of the list, and probably the reason for that is that he's just been in an awful lot of movies. So he probably is actually pretty well connected. The other people who are well connected, there's a bunch of famous people here: Donald Pleasence, Charlton Heston, Rod Steiger, John Gielgud. Notice that these are all sort of actors from a slightly older school of movies, and that's probably, again, just because they've had time enough to accumulate a lot of credits. They've just been in a lot of movies, so they're well connected. So this would be one example of one way we could sort of pinpoint important people in a social network by taking the network and analyzing it. It's actually not a very good way of doing it. So it has some disadvantages. One is that it's hard to calculate. In order to calculate the average distance from me to everyone else in the network, I need to calculate the distance from me to everyone else in the network, and it turns out that that's a pretty hard thing to do. I mean, of course we do this on a computer, you understand, but even so, a computer takes a long time to do this calculation, just because it's a very complicated calculation. Another disadvantage with it is kind of more subtle. It's nearly the same for everyone. Look at these numbers. Christopher Lee, 2.413, Donald Pleasence, 2.416. There's only a tiny difference there, a few thousandths difference. What that means is, if there was a small change in the network, you know, a node appears here, an edge disappears there, then these numbers would probably change a little bit. Not very much, but they only have to change a little bit, and it could upset the order. Maybe Donald Pleasence would leap into the lead. So you don't want to measure where your ranking of who's most important depends on tiny little changes in your network. So for that reason, this is kind of an unsatisfactory measure. So then the next question is, well, what can we do that's better? Well, there are various things we can do, but let me give you one simple example of something we could do. This is really a very simple idea, something called degree centrality. The degree of a node in a network is just how many other nodes it's connected to. So if we're talking about a friendship network, it's how many friends you have. If we're talking about the World Wide Web, it's how many links there are to your web page. So if you look at a network like this one, there's some nodes that have very high degree, meaning they have a lot of connections, and there are some nodes here or something that have low degree, meaning they have few connections. So degree centrality is just that number. It's just, let's say the most important people in the network are the people who know the most people. Very simple idea. But it's a reasonable one as well. I mean, you know, people who know a lot of other people could be influential. That's obviously an important thing. And the advantage of this is it's very easy to calculate. The closeness centrality that I just mentioned, it requires you to calculate the distance from you to everybody else in the network, which means you need to know everybody else in the network. With this degree centrality, you don't. In order to calculate someone's degree centrality, all you need to know is how many people do they know. Much simpler thing to calculate. You don't actually even need to know the whole network to do that. You can just, you know, measure this one person. That said, it turns out to be not entirely trivial to work out how many people somebody knows. It turns out if you just ask someone, how many people do you know, most people will get it completely wrong. I mean, if you ask people, you know, can you write down a list of everybody you know? most people could start writing down some names, but they'd run out of steam after a while. There's probably a lot of people that they know that they just can't happen to think of right at this moment. People are not good at doing this exercise. So instead, here's an alternative proposal that was made by two sociologists, Russ Bernard and Peter Kilworth. This turns out to work quite well. Give people a list of common surnames and ask them, how many people do you know with names on this list? That obviously doesn't tell you the total number of people that they know, but it's a sample of the people you know. If you then know, you gave them this many names, if you know how many possible names there are total, in the whole country, then you can scale it up appropriately. There's a fairly simple mathematical equation which tells you how to scale up that number so you can estimate the total number of people that they know. So I thought it might be interesting. We could try this exercise with the audience here in the auditorium tonight. You don't have to if you don't want to, but it's kind of fun and interesting what you get. Here is a list of the 48 commonest surnames in the United States. What I like to do, if you're okay with this, is we'll just take a few seconds, and I'd like you to go through this list and count how many people you know with names on the list. So here are the rules. If you know more than one person with a name, you count all of them. So if you know 2 people called Adams, you count 2. If you know 10 people called Adams, count 10. So you count everybody you know with a name on the list. And also, we better be careful about what we mean by know here. So let's say know means, if you saw this person walking down the street, you'd recognize them, you'd say hello, you'd greet them by their first name, they would know your first name back. Okay? So that's how well you have to know someone for it to count as knowing. I'm going to do this too. We'll take a few seconds here, and I want you to count how many people you know with names on the list. So here we go, starting now. See if you're still counting. I think I'm done. Give you a little more time. Okay. Are we good? No? You want a little more time? All right. 10 seconds more. 5 seconds more. 3, 2. Okay, very good. So those people are finished now. So now I'm going to take a poll. How many people knew between 0 and 10 people with names on the list? Okay, quite a few people, maybe 30 or 40 people. How many people knew between 10 and 20? Oh, lots there. Probably about 80 people in the auditorium. How many people knew between 20 and 30? Quite a few. 30 and 40. Okay, it's getting thinner now. 40 and 50. Still a few people holding out. 50 and 60? 1 or 2. 60 to 70. 1, 2, 3, 4. Over 70. How many people knew more than 70 people? Over 80. Over 90. Wow. Over 100. One person knew over 100. Just one person? No, 2 people. How many? 200. Wow. And someone back there as well. You have 150. Wow. Okay, so very good. So this is actually common. This is what you always find when you do this experiment. Most of us know, a modest number of people, 10, 20 or something with names on the list. But you usually find, in any crowd this size, that there are a few people that know a lot, 100, 200. Somebody knew 200 people with names on the list. And this is common with a lot of networks, if you look at the degree, at the number of connections that nodes have, that there are a few nodes, we call them the hubs in the network, that really have an enormous number of connections. And it turns out that those hubs in the network can play a disproportionate role in the behavior in the network. Even though there's only very few of them, it turns out they play a really very important role in the functioning of the network. So this measure of centrality, this very simple measure, just count how many people you know, actually turns out to be a pretty good one. It's pretty indicative of which nodes in the network are the ones that are really going to affect the system. Here's just one example of that. This is actually not a social network. This is the internet. This is the sort of thing you see. So this is just a bar chart of degree, in other words, of number of connections that nodes have in the network. So this is how many nodes have one connection. This is how many nodes have 2, 3, 4, 5. And you can see that it's falling off. But even when you get out here, there's still, 15 or 20, there's still a small number of nodes that have that many connections. This bit down here on the right we call the long tail. And that's where these hubs reside. There are only a very few of them in the network, but they can have this disproportionately large effect on the behavior of the network. So just to sort of illustrate that, here's an actual picture of the internet. And you can certainly see the hubs here. You can see them as these big, bright centers of activity. There's clearly something important going on here in the network. Those are the hubs, the ones that have a lot of connections. Okay, very good. So this is a really simple measure of importance in the network, one that's actually pretty effective. It gets over both of the drawbacks that I mentioned before for closeness centrality. The first one was that was hard to calculate. Well, this is much easier. We just did it. The second one was that the values are really close together so that the ranking might easily change. But with this degree, it's not true. You have somebody with 100 connections and somebody with 150 and somebody with 200. That ranking is not going to change. You might change those numbers a little bit, but it's not going to change who comes in first and who comes in second. They're well-spaced values, in other words. So it gets over that problem as well. However, it's not entirely perfect. Basically what degree is doing is it's giving you 1 point for everybody you know, right? It's saying, count up the number of people and you get 1 point for everybody you know. But when you think about it, that's kind of dumb, right? Because not everybody is equally important. And if you know the President of the United States, then that's way better than knowing just some average person, right? So a better way of doing this, slightly more sophisticated version of the idea of degree, is to give people more points if they know people who themselves are well connected. So there's various ways of doing that, but one way of doing it is a simple way. You just give each node a network score where instead of getting 1 point for each person you know, you get however many points they have. So you just add up the scores of the people that you know, and that's your score. Well, if you think about this for a moment, you start to see that there are some problems with this. In order to work out what your neighbor's score is, well, how do you work out their score? Well, they add up the scores of the people they know. And those people, they add up the scores of the people they know, and so forth. So it seems like this is never going to end. There's going to be sort of this infinite process of working out what everybody's score is just to work out what your score is. But it turns out actually that's not true. There is a clever mathematical trick called an eigenvector, which allows you to calculate all the scores just in one step, and you don't have to do this sort of infinite regression thing. So you can do this. This kind of score goes by several names, but one of its most famous names it's called PageRank. PageRank is actually a trade name that was given to this idea by Google Corporation. Google Corporation used exactly this idea, this PageRank idea, as a crucial, central part of their strategy for searching the web. When you do web searches on Google, they're using this kind of network idea, that your score is the sum of the scores of the people next to you. So how does that work? So here's a picture of a portion of the web, one of the pictures that we saw yesterday. So the nodes in the web represent web pages, and the edges in the web represent hyperlinks that link from one page to another. So Google's basic idea is we're going to work out which pages are important on the web by looking at how many links they get. If other people link to a page, they put a hyperlink from their page to your page, they went to the trouble of doing that, presumably because they think your page is good somehow. They think it's useful or interesting. Other people should have a look at it. So if lots and lots of people have linked to your page, that's a sign that it's important. But you can do a more sophisticated version of that idea by using this PageRank thing. We don't just say, oh, you get 1 point for each link. We now say you get some number of points that depends on how important the people who are linking to you. And how do we work out how important they are? Well, it's how many people link to them, and so forth. Back infinitely, but you can do this mathematical trick, this eigenvector, and work out those scores. Those are the PageRank scores. So now, here's how Google works. You type something into Google, for instance, you type in PageRank into Google, and it goes out and it finds a bunch of pages which might have something to do with PageRank. At this stage, they don't make any effort to work out which are the pages that you might find most interesting. Actually, they do kind of a deliberately bad job and net as many pages as they can. They just look for anything that might have the slightest thing to do with PageRank. That's why when you type in PageRank, you get 58,800,000 results, right? That's not because all of those pages are really relevant. You're probably not interested in most of them, in fact. But at this stage, we're just trying to find anything that you might possibly find interesting. But then, here's the clever bit, you take that huge number of pages and you print them out in order, putting the most important ones first. And how do you decide which is most important? You use PageRank. So in other words, you calculate the PageRank of those pages, you find the one with the highest PageRank, and it comes first in the list. So when you type something into Google, very often the page that you're looking for appears on this first page of 10 results that Google gives you for the thing you typed in. And that's because Google is not doing a particularly good job of finding pages. What's clever about Google is the order in which it prints them out when it finds them. And the way it does that is it uses the network. It uses this PageRank idea to work out which order to print them out in. And as you probably know, it's pretty effective. It really works. And makes Google a lot of money. Okay, very good. So that's centrality. That's one example of the kind of things that we can do once we have a bunch of network data. There are many other examples. I want to tell you about a few of them. Here's one thing that's kind of interesting, another very simple idea. If you look at a lot of networks, here's this is a social network. It's actually a collaboration network of scientists. But this is true of many networks. If you look at them, you find that there are a lot of triangles in the network. Triangle here, a bunch of triangles here, some triangles over here and here and here. Common thing in networks, you see there are triangles. So let's think, what does a triangle mean in a social network? A triangle means, one way of putting it would be to say, the friend of my friend is also my friend. So I know someone, they know someone, and I know that someone, so the three of us form a triangle. Or another way of saying it is, I have two friends, and they're both friends with each other, so the three of us form a triangle. Either way. So you've got some node here, here's me in the middle, I have a bunch of friends, and at least some of my friends know each other. This idea goes by the name of transitivity. It's a word we borrow from mathematics. Transitivity is this idea that the friend of my friend is also my friend. A and B and C means also A and C. So there's a friendship between A and B, there's a friendship between B and C, that means there's also a friendship between A and C. That's the idea we call transitivity. So it's kind of a fancy word. All it means is the friend of my friend is also my friend. Now imagine, so one thing that can happen in a network is that my friends are not friends with each other. So this is sort of the alternative to this would be something like this. Here's me, I have a bunch of friends, but there's now no connection between my friends. So there's gaps here where I would expect there to be an edge. In the social networks literature, they sometimes call those structural holes. It's a fancy name for just saying my friends don't know each other. If you talk to a sociologist about this stuff, they would say that indicates that this person here in the middle has more power and influence because their friends are not connected to each other. That means that they act as the broker between their two friends. Those friends don't know each other directly, so information flow or contact between those people has to go through them, and that gives you more control, more influence, more power. That's very sort of typical sociologist speak. They're also always worrying about sort of power and influence in networks. The thing that I want to talk about actually is a much simpler idea, and it's this. It's just the idea that if you look for people who have a mutual friend, that's an extremely good predictor that they will become friends in the future. That may not sound like a big revelation. It's pretty obvious, you know, the friend of your friend is somebody you're likely to meet at parties or something like that. But it turns out to work really well. If you actually want to predict who's going to be friends with whom in the future. This is an extremely effective way of doing it. Here is an example. This graph comes from a paper that I did a few years back, and this is actually for a scientific collaboration network of the kind that I showed you before. So this is who's writing papers with whom, and I'm going to try and predict who's going to write papers with whom in the future. So what this shows is I take two people and look at how many common neighbors they have in the network. In other words, they haven't written a paper together yet, but they've both written papers with some other third person. Or maybe they've written papers with two other people or three other people. The person who has written, the two people who have one common neighbor in this network, who've written a paper with the same person, it turns out, are 45 times more likely to collaborate in future than two people who don't have a common neighbor. People who have two common neighbors are over 100 times more likely to collaborate in the future. So this is a huge effect. This is a very effective way of predicting something that's going to happen, and it's just using this very simple network property, which sort of seems obvious in hindsight, but even it's obvious, it can still be useful if this is something you want to predict and you have the network data. Then this is a very effective way of predicting who's going to be connected in the network in future. Okay, so this is a simple example of sort of a structural network property that you can use to predict things. Here is another example of a network property that's very useful for a lot of things. It's a property called homophily. Here is a picture that you saw yesterday. This is one of Jacob Moreno's hand-drawn social networks from his book that came out in 1934. And as we said yesterday, this particular picture represents a pattern so the nodes here represent elementary school children playing in a playground, and the connections between them are which kids are playing with which other kids. And you immediately see, when you look at this figure, that there are two basic groups. They correspond to the boys and the girls. The boys are mostly playing with the other boys, and the girls are mostly playing with the other girls. This is the effect that sociologists call homophily. That just means you like people who are like you. And this is a very common effect in networks, that the connections tend to be between people, or more generally between nodes, that are similar in some way. So here, most of the connections are either between two boys or between two girls. They tend to play together in their separate groups. This is something that turns up very often in a lot of different networks. I'll give you a bunch of other examples. Here's a sort of modern-day example of the same thing. This is a group of high school children. This is data taken from the Ad Health Project, a big NIH project on social networks in US high schools. And again, in this high school, you can see, so the nodes are the kids in the school, and the edges are who's friends with whom, and you can see that it splits up into two clear groups here. But now this is a high school, and in the high school, the boys and the girls are often friends by the time they're this age. So these groups are not actually groups of boys and girls. These groups, it turns out, are divided by race. There's a group of white kids here and a group of black kids here, and the white kids are mostly playing with other white kids, and the black kids are mostly playing with other black kids. So this is a similar sort of effect. It's still homophily. People prefer to be acquainted with other people that they perceive as being similar to them in some way, but it's homophily by a different thing. Previously it was gender. In this case it's ethnicity. Here's another example, also taken from the Ad Health data. This is who's friends with whom by age, or actually technically by grade, but it's roughly the same thing. Each dot on this plot represents a friendship between two kids. And the age of one of the kids, well, the grade of one of the kids is along here, and the grade of the other kid is here. And what you see is that most of the dots sort of fall along this dark band diagonally down the middle. That's telling you that people in 9th grade are friends with other people in 9th grade, people in 10th grade friends with other people in 10th grade, and so forth. Obviously, not a big surprise if you've ever been to high school, but it's showing you that people tend to be friends with other people who are about the same age as they are. Here's another example of a similar thing. This is who marries whom. This plot, each dot shows one couple in a study, a large study of US couples called the National Survey of Family Growth. So each dot represents one married couple, and the position of the dot tells you the ages of the man and the woman at the time they got married. So age of the husband along the horizontal axis, age of the wife along the vertical axis. This vertical axis only goes up to 40. That doesn't mean that women don't get married after age 40. It's just that in this particular study, they only interviewed women up to age 40. So that's why it stops there. Some of the women they interviewed were married to men over age 40, so that's why the male axis goes on a little bit further. But again, what you see in this plot is that most of the dots lie along this sort of diagonal band here, indicating that people are primarily getting married to other people around the same age as they are. Again, probably not a big surprise, but it shows there is homophily in this network. Well, technically, actually, who's married to whom is not really a network, because, you know, in principle, you're only married to one person at a time. So it wouldn't actually make a network. But I'm sort of thinking of this as a proxy for who's friends with whom. I mean, presumably you're friends with your husband or your wife before you get married to them. So this is an indication, again, that people tend to be friends with, acquainted with, other people about the same age as them. Okay. Here's another example. This is just, I just wanted to give you one non-social network example. This is a World Wide Web example. This is from a study by my Michigan colleague, Lada Adamick, and her collaborator, Natalie Glantz. And they were studying weblogs, or blogs for short. Blogs are personal websites on which people post their opinions about anything they want to. But in this particular study, Adamick and Glantz were studying political weblogs. So these are blogs on which people write stuff about their political opinions. And the blogs that they studied divided into two broad groups. There were liberal ones in blue here on the left, and there were some conservative ones in red here on the right. And then the edges, again, are hyperlinks that link from one blog to another. And what they discovered is that overwhelmingly, the liberal blogs are linking to other liberal blogs, and the conservative blogs are linking to other conservative blogs. So again, it's as if conservatives like to be connected to other conservatives, and liberals like to be connected to other liberals. Okay, so that's the basic idea of homophily. How can we use this to make predictions about what's going on in the network? Well, here's a very simple example. Consider again this network here of kids in a high school. If I were to take one of the kids in one of these groups, say a kid over here, one of the black kids, and look at their friends, I would find probably that their friends are overwhelmingly black. So if I just took a simple majority vote, just took some random kid and looked at their friends and took them a majority vote of whether they're black or white, that's a pretty good predictor of whether the kid themselves is black or white. And it turns out that works very well. If I just take a simple majority vote, I get it 83% right in this particular network. Well, that's not a big feat. I mean, it's not really that difficult to tell whether someone is black or white, but there are other things that are a bit harder to tell. For example, voting behavior. It turns out that, on average, about 70% of your friends vote the same way as you do. So if I just took a poll of all your friends and just took a majority vote amongst your friends, I could probably predict pretty well how you are going to vote, just by knowing the network structure, knowing who you're connected to, and knowing how your friends vote. So here's some statistics. So 70% of your friends vote the same way as you do. 79% of people are within 5 years of the age of their spouse. Okay? So people are marrying other people of the same age as they are. In that high school example, turns out about 67% of friendships are between people in the same grade. In the same high school study, 83% of friends had the same ethnicity. A similar result, this is from a study of couples in California that was done in the 1990s. They found that 72% of people were the same ethnicity as their partner. In the web example that I showed you, the political weblogs, 91% of the web links in that web example were between blogs of the same political persuasion, either two conservative blogs or two liberal blogs. So these look like pretty impressive results, but we have to be a little bit careful here. Just giving you that raw percentage actually doesn't tell you as much as you might think it does, because if people just sort of chose their friends totally at random, then there would be some chance that they would choose people who were the same as them, just by random chance. So to give you an example, if you were talking about the kids in the high school, Well, there's 4 grades in the high school, 8, 9, 10, 11, 12, and about a quarter of the kids in each one. So if you just chose your friends totally at random, about a quarter of the time you'd pick people who were in the same grade as you. So we wouldn't be surprised if we saw that 25% of friends were in the same grade. We'd say, oh, well, that's just what we'd expect if people chose their friends at random. So what we do is we say, well, we expect 25% of them to be friends in the same grade. What we observe is that 67% of them are in the same grade. And what we calculate is something called the modularity. It's just the difference of those two numbers. So small bit of math here, but very simple. We just take the 67% and we subtract the 25% that we can already account for because it's obvious. And what we're left with, that's the bit that we're interested in, 42%. 42% is a reasonable number. That tells you that there's a real effect going on here. It really is true that people prefer to be friends with people in the same grade by a sort of 42% overage above what you would expect if they just chose their friends from all of the grades. So this is a quantity that we call the modularity. Here's a couple of other examples of it. I told you that 79% of people are within 5 years of the age of their spouse. But it turns out that if people just married other people completely at random, 66% of them would be within 5 years of the age of their spouse. Why so high a number? Well, it turns out actually that most people get married between the ages of 18 and 25. So most people within a very narrow age range to begin with when they get married. So if they just chose someone at random, probably that person is going to be around the same age as them anyway. So most people, even if they just chose their partners at random, would be within 5 years of the age of their spouse. So now you calculate this modularity thing, 79% minus 66%, you get only 13%. And that's telling you that actually that result wasn't particularly significant. There wasn't anything very important going on there. So ignore that one. But this one down here is pretty good, actually. This is from the California study of couples. We said that 72% of them were the same ethnicity as their partner. If it was just completely random who they chose, it would be 29%. So the difference is 43%, which is pretty significant. It's telling you that there really is a significant preference there for people to have a partner of the same ethnicity as them. Okay, so this gives us a way of measuring this homophily effect in networks. What I want to do now is, it's going to seem like I am going to change subjects and talk about a completely different thing, but actually it's not completely different. It'll come right back to this idea here. This idea turns out to be the sort of central idea behind another very clever idea in network theory. Suppose I have a network that looks like this. Many networks actually have this kind of structure. They have groups or communities in the network, meaning, there's a clump of people here that all know each other, and there's a clump of people here that all know each other, but not many people know each other between the two groups. This is a common thing that we see in a lot of different networks, and I'll actually show you some examples in a moment. So one of the things that people sometimes ask about networks is, are there communities in my network, and if so, can I find them? Turns out this is very useful for predicting things in networks. As I say, I'll show you some examples. But so here's what the trick we want to do. We want to take a network and find the groups in it. But when we think about it, that's kind of similar to what we already saw with this homophily thing, where you had, for instance, 2 groups in this high school friendship network. We have a measure, this thing called modularity, which allows us to say when we have a lot of homophily in our network. So what we're going to do is we're going to co-opt that idea and apply it to finding these communities in the network. So the way this is going to work is, suppose you have some network and you don't know if there are communities in there. But if there were communities, if there was some division, say, into 2 groups, and I could find that division, well, now let's call the people in this group type 1 people, and the people in this group type 2 people, and then let's measure the homophily of the network. Let's see how strong an effect is it. Is it really true that mostly type 1 people want to be friends with other type 1 people, and type 2 people want to be friends with other type 2 people? If that were the case, then it would be telling us that we have groups, just like we do down here in this high school network. So we don't actually need to know what the types of the people are. We just call them 1 and 2. All we need to know is, if we knew what the groups were, we could go calculate the modularity, and it would give us a high number, telling us, yes, we found the right thing. We found the groups in the network. We found two groups where most of the connections are within the groups and very few connections between the groups. So the way this works is you take some network, and you don't know how you're going to have to split it up to get the groups. So what you do is you just split it up in every possible way. For each one, you calculate this number, the modularity, and then you look through all of them to see if any of them have a high score. And if they do, then that's the way you should divide up the network. That's telling you that's where the groups are. This is called an optimization method. There are various standard computer techniques for doing this. All you need to know is the definition of this modularity function and your network, and then your computer just goes to work, looks at every possible way of dividing up the network to find one that gets a high score. So let me give you some examples of this in practice. This is a famous network from the social networks literature. It goes back to the 1970s. This is another network of students. It's students in a US university now. What this network represents is, it comes from a study of a karate club in a US university, so a place where students go to practice their karate. It was done by a guy called Wayne Zachary, who apparently, he's an anthropologist, apparently spent about 2 years studying the social dynamics of this particular karate club at this university, and amongst other things, worked out, who was friends with whom, so he could construct friendship networks like this one here. Then an interesting thing happened. During the course of his study, a dispute arose within the karate club. It was actually about whether they should raise the fees. It doesn't really matter what it was about. But there was this dispute. One faction wanted to raise the fees, another faction didn't want to raise the fees, and eventually the club just split in two, and half of the people in the club went off and started their own club. This network that I'm showing you here is a friendship network taken from that study. This friendship network, crucially, was measured before the split happened. So this is the pattern of who was friends with whom in the original club before it split up. So what we do now is we take this network and we feed it into our computer program that does the community finding calculation that I just described. And what does it do? It says, oh yes, actually there are communities in this network, meaning there's one possible way of splitting up the network that gives us a high modularity score. And that possible way is the one indicated by this divide in the picture here, this dotted line down the middle of the picture. It turns out that that division is exactly the same as the division that happened in real life when the club split into two parts. So this computer program is, in a way, predicting what's going to happen. Because remember, this network was measured before the club split up. And from the patterns of who is friends with whom before the club split up, you can already see the future of what's going to happen when it splits. The computer program accurately predicts from the structure of the network how it's going to split up when it does it. Here's another example. This is from work I did. I mentioned this yesterday, that I had done some work with marine biologist David Luceau on social networks of bottlenose dolphins. So dolphins are very social animals. They have well-defined social networks of which dolphins are friends with which other ones. This is a network that comes from David's work with a school of dolphins in Doubtful Sound, New Zealand. There are 62 dolphins in this network. This is one of the friendship networks that he constructed for those dolphins. And again, during the course of the study, an interesting thing happened. This dolphin here in the middle, represented by the yellow triangle, disappeared. We have no idea where it went. It wasn't dead because it came back about 2 years later. So in the meantime, who knows where it went? But the interesting thing was, when that one dolphin disappeared, the whole school of dolphins split into two separate schools. Apparently, that one dolphin in the middle there was just the glue holding the community together, and once he was gone, the thing split apart. The two colors here, red and green, indicate the way the school split in real life, as observed by David. This dotted line is what you get if you feed the network into our computer program. So in this case, you'll see that it hasn't done it perfectly correctly, right? It's got a few dolphins that are on the wrong side of the line. These green ones here actually went with that half of the group and not with that half of the group, but it's pretty close. Again, it's predicted pretty well how the community of dolphins was going to split in two based just on the observed social network of which dolphins were friends with which. So this tells you a couple of different things. Firstly, it tells you that we can actually predict things using knowledge of the networks. It also tells you, and this is kind of an important realization, that these social networks really are affecting sort of the dynamics of people or dolphins or whatever it is. Social networks are having an important impact on the way people behave because they're going with their friends when the thing splits up. In the case of the karate club, for instance, people may have had opinions one way or another about whether they should raise the fees, but what actually happened when the network split is that people stuck with their friends. So whatever people originally believed about one thing or another, when it split, what was more important is who are you friends with, and I want to be in the group with my friends. So these friendship networks are dictating the dynamics of the network, and by knowing what the friendship networks are, we can predict what that dynamics is going to be. In the last couple of minutes, let me just give you one more example. This is a non-social example. Here is a network constructed by my friend Valdis Krebs. It's a network of books. These are books about US politics published around the time of the last but one presidential election, so the one between Bush and Kerry. And Valdis has conveniently color-coded them, blue here on the left and red on the right, to indicate their political persuasion. So for instance, over there on the right you have the faith of George W. Bush, and over here on the left you have the lies of George W. Bush. And then in the middle there are a few sort of purple books which are kind of somewhere halfway in between. And then what are the edges? What are the connections between books in this network? Well, they are frequent co-purchasing on Amazon.com. If you buy books on Amazon, you look up a book, it says, people who bought this book also bought these other books. How does Amazon know that? It knows because it has all the purchasing records. It's seen many people buy these two books together. So what Valdis did is he just went and looked up each of these books. There's about 100 of them here, and he looked at which ones were frequently bought with this other book and put in the connections here. So the connections indicate which pairs of books people are buying together. So now we take this network and we feed it into our computer program that detects groups or communities within networks, and what we find is two big groups of books, one over here, which I've conveniently color-coded blue, and the other one I've conveniently color-coded red, and it turns out that they correspond very nicely to the liberal and conservative books in this study. And so I could, for instance, use this to predict what kind of books people are going to read. If they've read one of the red books before, then it's very likely they'll read another red book, but very unlikely that they would read a blue book. And similarly, if they read a blue book before, it's very likely that they will read another blue book. So again, this sort of community structure in the network can predict things that people are going to do. Very good. So today, what we've talked about is, if I have a network, how can I analyze that network and tell things about what people are going to do, or what dolphins are going to do, or what the web is going to do? I can guess which people will be most influential by calculating centrality measures. I can guess who people will be friends with. There'll be people friends with people who are in the same grade as them, or something like that. I can guess what books people will read. I can guess who they're going to vote for. I can guess who they're going to marry, to some extent. There are other things, however, that we can do with networks. These are all things that are just using sort of the static structure of the network. All I take into account is sort of what is the shape of the network. How many connections do you have on the network, or something like that. However, there's a whole other class of things that we're interested in to do with networks, which is processes going on networks. The network acts as a conduit for all sorts of things spreading through communities. News, rumors, fashions spread over social networks of who knows whom. Diseases are another example. They spread over networks of who's had contact with whom. Once you know what the structure of a network is, perhaps you can predict how the disease is going to spread. If you can do that, maybe you can even work out some effective way to vaccinate a community to prevent the disease from spreading. All these are ideas to do with the spread of things on networks, and these are the topics that I will talk about tomorrow in the last of these 3 lectures. However, for the moment, I'm out of time, so I'll shut up now. Thank you all very much for your attention. I'd be happy to answer questions. Any questions? Yes, one back there.
I'm very impressed with your research, and thank you so much for making it so lively.
Thank you.
I'm also curious about the nodes that intersect in the groups that are not connected, the non-homophilous groups. For example, what makes, are you doing any research on what makes the people who buy the red books maybe cross-link over to the blue books, and or the kids who have interracial friendships but they aren't part of their group? What about those anomalous cases?
Okay, so that's an excellent question. So I don't know the answer to that question. That's not something you can tell directly from the network. The network allows you to see these effects and quantify these effects, give actual measurements of them. It doesn't tell you what the reasons are for these effects going on in the first place. However, what a lot of people are interested in doing is, and I mentioned this briefly yesterday, is often when you do these studies of networks, you measure a lot of other things in addition to measuring the network. So you ask people who are you friends with, but then you ask people a lot of other things. So for instance, that Ad Health study of the US high school kids asked a lot of questions about, what after-school activities the kids indulged in, and they would ask, what are the age of your friends and what things do your friends do, and so they're trying to get at the reasons why people were friends. So in principle, there is data there that you could look at. So you could look at some non-homophilous friendship, friendship between two kids in different grades or whatever, and you could ask what other things between them could have been responsible for this. So, usually friendships do form because people have things in common, but it's certainly possible for them to have some things in common and some other things not in common. So what you may be seeing is the things they have not in common, and then some other thing there that they have in common that's the reason for the friendship. So in principle, those data are there, so people sort of realize that there's this issue and are measuring those things. But in this particular case, I can't actually tell you what the answer is. That's not something that comes from the network itself. Yes, question back there.
Did you do any studies of what happened when the lone dolphin came back and how the two groups interacted?
So excellent question. So first of all, it wasn't me. It was David Luceau who did the actual studies of the dolphins. So the lone dolphin did come back, and indeed, when it came back, the two groups fused together into a single group as well. By then, the network wasn't exactly the same as it was before this fission, where they divided. And that's in part because some other dolphins had been born and some dolphins had died in the meantime. But the fused network afterwards was actually quite remarkably similar to the one that had been beforehand. So it really seems like the yellow triangle in the center of the picture there was somehow sort of the fulcrum holding these two groups together. When it went away, they split up. When it came back, they came back together again. So yeah, it seems like it was really quite a repeatable experiment in that sense. There's a question over here. Yeah, so fair question. It's predictive in the sense that the data on the network were measured before the split happened. So if somebody had said, I think this is going to split, how is it going to split? Then we could have fed this into our computer program and made a pretty good guess about how it was going to split. However, two caveats. First of all, nobody did ask us that. We can't predict that it's going to split. All we could do is predict how it was going to split. And second of all, of course, I'm showing you this example because it worked. If it hadn't worked, I probably wouldn't have shown you this one. So we should be a little bit careful about that. But good question. Yes, question back there. Well, so that's also a good question. So Amazon does not share with us the details of how it does those calculations. So, for obvious reasons, that's some proprietary thing. So we don't know how accurate those, people who bought this book also bought these other books are. But the assumption is that it's based on co-purchasing data, and hence they're not actually making a guess about whether this is a conservative book or a liberal book. They're just looking at what books are bought together. And I find it very reasonable to suppose that you can do that books of the same political persuasion are commonly brought together, and therefore you don't actually need to cheat and know about what political persuasion the books represent in order to do this accurately. And indeed, given that Amazon sells millions of books on its website, it really wouldn't be very practical for it to try and make value judgments about the content of books and then link them together by hand, because it would just be an enormous amount of work. It's certainly in Amazon's interest to develop these clever algorithms that use the network structure and work out which books are connected together in some automated way so that the computers can do all the work and you don't need to do these kinds of things by hand. So it's a fair question. We don't actually know how that worked, so we don't know for certain that there wasn't some hand tuning going on there. But I think it's probably the case that it was just frequent co-purchasing that went into that. Yeah? Oh, a good question. So they actually do know the genealogy of most of the dolphins, not by genetics, but just by either watching mothers give birth to the dolphins or mostly by behavior afterwards. Apparently there's quite an extended period when the offspring hang out with their mother, and so there are groups within the social network that correspond to who's descended from whom. And it actually turns out, so we did some of this in the paper that we wrote about this, that you can also ask not just about the two big groups that the community splits into, but also there are smaller splits within those groups, and it turns out that those are mostly upon matrilineal lines, meaning that the offspring of a particular mother tend to be friends later on in life. So they do know those kinds of things, and there's evidence that that does affect the shape of the social network later on in life. Yeah, question right at the back there.
Two-part kind of thing here. Do you know why it's Kevin Bacon?
I don't know for certain why it's Kevin Bacon.
Separation.
Maybe. So the apocryphal tale is that this game was invented by two college kids from somewhere or other, and their claim was that Kevin Bacon was the center of the movie universe, and the way they were going to prove it is, look, you can get from any other actor to Kevin Bacon in just a small number of steps. And of course, this is a completely ridiculous assertion, because you can take any other actor and do exactly the same trick with it, and it'll work just fine. And moreover, Kevin Bacon is not even the most central actor in the network in this sense. As you saw, actually, it should really be the 6 Degrees of Christopher Lee, because he's the one who's really the center of the network. So yeah, why they chose Kevin Bacon, I really don't know.
Rhymes just said separation.
Yeah, maybe it was just for that reason.
If we're predicting these futures, are we changing them?
A good question. So in some cases, yes. I mean, in some cases, whatever we do with people's social network, they're not going to care about. But there are other cases where knowing things about what's going on the network do change the structure of the network. There's some feedback there. So one of the things that you notice, for instance, is, so I talked about this homophily effect, that people tend to like to be friends with other people who are similar to them. But it's also true that people tend to form opinions that are similar to those of the people they're friends with. So there's a bit of a chicken and egg problem here. How do you know which came first? So if you're talking, for instance, about voting behavior, it's certainly true that most people vote like their friends. But is that because they became friends with people who are like-minded, or is it because they adopted opinions from their friends? Probably, in fact, both of those things are happening. People change their opinions to match their friends, and people change their friends to match their opinions. So both of those things are affecting each other, and the structure of the network itself is certainly being affected by sort of what's going on the network. There's another question in the far corner there.
I was wondering if the predictive ability of these networks can help model neural networks. Could it only do a worm? Could it do a human?
So I think, so first of all, I'm not a big expert on neural networks, so I should be careful what I say, but my main feeling is that these kind of statistical techniques are probably not going to tell us very much about neural networks. And the reason is that the things we're interested in neural networks are how sort of particular circuits in the network achieve the things that they do. So we're really interested in the details of the network. Whereas with a lot of these networks that I've been telling you here, it's more a sort of big homogeneous thing. Every node represents a person. Of course, people are different, but in some sense, it's sort of all the same. And then these kind of statistical techniques turn out to give reasonable results. There are certainly people who try and do these things with neural networks, and it's certainly, I think it's probably possible that there are some structural results you could get out like that, but I think the really big questions about neural networks, like how do we think, have to be solved by some other techniques. So I'm a little bit cautious about how far you can take these techniques in the case of neural networks.
So we have time for one more question.
Okay, maybe a question over here.
Are you aware of any political organizations that are making use of network science?
Well, so no, I don't know of that, but certainly there are people who are interested in analyzing political networks, and I mentioned a bit about this in the question and answer session at the end of last night's lecture. So certainly people have studied political networks, things like which politicians sit on committees with which others and which co-sponsor bills with which others and things like that. And you can use this, for instance, to do things like predict how people will vote on certain measures, or to rate politicians according to some sort of political spectrum, how far are they to one side or another side. So there are definitely people who are interested in political networks of one kind or another and are doing interesting things with them. However, I don't actually know of any specific examples of the things you say of a political organization using this for something. So, yeah. Thank you.